next lecture. So in this lecture, we would be covering the logistic regression. So as you know, the logistic regression is basically an unsupervised learning model, which basically allows you to predict certain labels, which could be yes and no. And let's take an example of what type of labels we can be predicting over here. So we can predict whether a person is a male or a female, whether the email is a spam or not spam, or a person is likely to say yes or no for a given decision, right? So predicting whether an input belongs to which class falls into two categories, which is basically yes and no, and we call it as a binary classification. So as per the binary classification, we can have a decision as a 0 pointing to no and 1 pointing to yes. So let's assume we have a hypothesis and we are trying to predict a gender, right, based on their height and weight. So in that scenario, we are likely to take all the feature sets of that person, and using the logistic regression, we should be able to predict whether that gender has a probability of being a male or a female. All right, so a 0 would point, as I said, as a false category, and a 1 would falls to a true category. All right, so as far as the classification is concerned, predicting what class an input belongs to is extremely useful in many problems, such as determining whether someone can be approved for a loan. So let's say you go to a bank and you want to get your loan application to be approved. They're going to see certain features. What's your income, whether you're married, or whether you're a graduate from the school. All those features should be considered as part of predicting the labels whether you're qualified for that loan or not, right? So logistic regression are not just limited to binary classifications also. In fact, they can be extended to multiple classes. Example, predicting the handwritten digits, right? Predicting the article categories, whether it's sports, politics, health, or also you can use them to predict the level of risk involved in investments, right? So now look at the expressions that goes behind the logistic regression. So if you remember from the previous lectures in the linear regression, we know that a function can be represented as, for all the feature sets that we're including, all the x variables, we associate certain weights to them and add a bias, which is a constant value over here, right? So that particular expression using a sigmoid function is represented as shown in the screen below, which is 1 divided by 1 plus e to e raised to power minus z. So this, and how do we really look at this expression in terms of the binary classification? So let's look at the next slide basically. So if you see in the right hand corner, I have a screen. If we have from our equation all the value sets and we plug those values in this expression of a sigmoid function, then those values would fall on the curve that's ranging from -6 in the lower left hand corner to the upper right corner that moves the values between 0 and 6. And assuming certain values fall um, at certain point in this graph, and if that value is less than 0.5, we can treat the probability of that particular decision or a label that we're predicting is less than 0.5, which means it should be treated as a zero value. And if the probability is greater than 50%, we will make sure that its likelihood to be is a different level, which is level 1. So that's how, using the sigmoid function, we can predict whether the particular label is going to fall into category 1 versus category 2. Also, logistic regression creates a decision boundaries. So in this picture, you can see that we have uh, a student being admitted to the school, and we are using the logistic regression to plot the decision boundaries over here. So these decision boundaries gives an idea of linear separation between the values. If you see the upper uh, dots that's beyond the boundary line, it basically shows the decision whether the students are admitted or not. So the upper part, if you see on the right hand corner, shows that the students are admitted. Those are, um, you know, purple color dots, while the crosses shows that students who appeared in the exam are not having the highest score enough to be qualified, and that's why they fall into decision level of 0. That means they never qualified for that particular college based on the exams. So that's how we can use the logical regression to really predict the labels. And let's now take a deep dive into one of the example of building a logistic regression labels as part of exercise. Thank you, and thanks for joining this lecture. Welcome, friends. So this lecture is about the case study for predicting the fraud on the credit card transactions. So in order to start, I will import the generic packages, which is NumPy, Pandas, Matplotlib, Seaborn. Let's import these packages, followed by I'm going to be importing certain classifier libraries. So for that, I'm relying on logistic regression, that importing from linear model. I'm also taking support vector from SVM. Um, the next classifier is k neighbors classifier, which I'm importing from sklearn.neighbors. Let's also import decision tree classifier from sklearn.tree and have a random forest classifier as well. That would be an add-on from sklearn.ensemble. All right, so once we are done with this, we would need other libraries. In order to train test split the data, I need the package, and I'm importing that particular package from model selection. I'm also importing accuracy scores from sklearn.metrics and other scores like F1 score, recall score, precision score, all that coming from the sklearn.metrics. In order to do the cross validation, I'm importing two different packages over here from sklearn.model selection, that is kfold and stratified kfold. Also import let's warnings just to override any warnings if there are, right? So now let's import the data set, and for that I'm importing the credit card.csv file, which the data set we imported from downloaded from the Kaggle. So we should be able to do pd.read.csv, and let's run this cell. Let's see the output of this cell. Um, okay, so I'm going to go back and run this cell. So I have the output of this cell, which is I got all these anonymous columns V1 to V28, and I have additional columns like amount and class. Since the data is anonymous, so we don't know these columns exactly, but at least we know that the class has the labels 0 and 1, so we should be good with that. That gives an idea of whether the transaction is non-fraud versus fraud, and amount is basically the customer paying on the credit card transaction. All right, so okay, so we have the data, and now let's do a simple step, that's df.describe. That should give us the full distribution counts, min max values of each variable. Okay, so I can see all these variables with the first quartile 25% for V1 minus 9 value, and the third quartile is 1.3, max value is 2.4. Likewise for V2, I can see minus 5.9 as the first quartile, minimum value is minus 7, and the third quartile is 8. So I think what we can estimate from here is there obviously supposed to be correlated data, non-correlated data in the data set, and also a bunch of outliers. So in order to rely on our data that can be used for predictions, we should rely on the data that falls in the first quartile, that is 25%, and the third quartile. Anything lower than first quartile must be treated as an outlier, and anything above the 75%, which is the third quartile, must be treated as outlier. Okay, So what I'm going to do is I'm going to wrap up this lecture over here, and I will see you in the next lecture. Thanks. So welcome back to this lecture. So in the last lecture, we left at this particular cell where we were able to run df.describe, and we have the results as showing for each column the min max values in the first quartile and the third quartile, right? So let's now look at some of the sanity of the data. So for that, I'm doing a check on the nulls. I'm running df dot is null dot sum dot max. If I run it, I get results as 0, which means none of the column is having null values. And obviously my columns are list of columns are df dot columns from time v1 to v28 amount in class. So we are aware of 3 columns which we can pretty much read. Rest of them are anonymous, so we need not to worry about them as of now, but obviously we would be able to interpret the negative correlations and the outliers in those columns. So that would be our objective. So now let's print the percentages of the classes as fraud versus not fraud. So for that, I'm doing a print statement, and on the df class, I'm doing a value count with the index of 0 divided by the total length of the data frame. And if I multiply by 100 comma 2, that's for the precision, I should be able to get the non-fraud transaction. Similarly, for the fraud transactions, I'm taking df class dot value counts with the first index and divided by the total length of the data frame multiplied by 100, and a precision of 2 should give us. So once we run this, we're able to view that 99.83% of the data is non-fraud transaction, and only a fraction, which is 0.17% of the data set, is a fraud transaction. Okay, so let's do the count plot as well, so we can see this instead of just the percentages. So for that, I'm using cbond sns.countplot. For the class variable, I'm using data is equal to data frame, and let's print the title plt.title. For class distribution, no fraud present versus the fraud detection. So once I run this, I should be able to see this result, and the result shows roughly around 280,000 records coming in the bucket of non-fraud versus 400 odd records are coming in the fraud transactions. Okay, so let's move to the next thing. So now let's review the distribution of the amount column and the time column so that we can find any outliers related to those particular columns. So let's start with the subplot. So I'm doing a subplot on x-axis. I need 2 figures, so I'm doing 1 by 2. Figure size is 20 by 10, and let's store the amount from data frame amount dot values into the amount column, time dot values in the time column, and let's do the distribution plot. So sns dot distribution plot on the amount value. X-axis, I'm taking the first index ax0 because I want the amount value as the first figure. So on x-axis, the first index would be 0 and the color is red. Let's set the title for ax0 dot set title distribution of the transaction amount, and let's set the limits. So ax0 dot set x limit, so minimum amount value and the max amount value. Similarly, we will follow the same pattern for the time value. So let's do sns dot distribution plot time value. X-axis is ax1, the second index, which is 1 over here. Color is equal to blue. Let's set the title ax1 dot set title distribution of transaction time, and ax dot set the limits. My limits are lower limits and upper limits, which is going to come from minimum time value and the max time value using these functions. And let's do the plt dot show. Okay, so what we see the results, we see there is a distribution of the amount value, which obviously in the left figure has slight number of outliers. We should be able to remove those outliers. And the second image about the distribution of the time transaction value. All right, okay, so I think this is wonderful. So we're going to proceed in the next lecture, and we will continue the exploratory data analysis part of this course. Thanks for joining this lecture. Welcome back to this lecture. So in the last lecture, we have seen the distribution plot for the amount value as well as the time value. And we did discuss about that the transaction amount has some skewness, and that's what we should be working on. So before I deep dive towards removing the outliers, let's understand how we're going to scale the data and different type of scaling techniques. So in this lecture, we would be starting with the robust scaler. The reason being, we understood that there is the outlier in the data set. And since we have three different type of scaling mechanisms, we have standard scaler, min-max scaler, and robust scaler. So let me give you a brief introduction of that. So standard scaler follows the standard normal distribution. That means it will scale the data and will take the mean and scale the data to its unit variance. That's what the standard scaler does. I'll also take an example to give the illustration for the difference between the three different standard scaling techniques. And let's look at the min-max scaler. It's basically scales all the data features in the range between 0 and 1, and if there's a negative data, then it basically scales the data between -1 and 1. But the hindsight of these two scaling techniques is that if there are outliers, then they do not guarantee the balanced feature scales. And because of the influence of the outliers, the empirical results may not match with respect to the quality of the accuracy score that we're expecting. So while in the robust scaler, we first remove the outliers and then apply the standard scaler. That's what the robust scaler is. So basically, it sits on top of the standard scaler, right? So what I'm going to do is I'm going to take this into a little bit more in terms of an example. So let's take a review of those three different scaling techniques in the next lecture. I hope we are enjoying this case study, and I'll see you in the next lecture. Thanks for joining. So in this lecture, we will be discussing about the difference between the standard scaler, min-max scaler, and robust scaler. And let me give you a quick introduction of an example where you can understand how robust scaler is different than the standard scaler. So we start with a reference link where I'm just checking this example for you guys to give you illustration. So let's import the packages pandas, numpy, and preprocessing package by sklearn and matplotlib, right? And also import the SNS package from Seaborn. Okay, so let's create the very first step is to create this a data frame. And the way we're going to create a data frame is by creating two different columns, and we are leveraging np.random.normal to get a distribution of the data, which provides us the very first line. If you see x1, that we're creating a column is creating a distribution of the data which is having lower outliers, while the x2 column is having higher concentration of the outliers, right? So that's the intent, to be able to make sure we can remove the lower outliers, which is the first quartile we have been talking about in the example, and the higher quartile example, the third quartile, 75th percentile and above. If we have something, then we should be able to remove that data which is not forming the pure set of our data set as part of the features. Okay, so we have the next step as basically calling the robust scaler. So we're calling preprocessing.robust scaler and assigning an object scaler for that. And after that, we would be doing fit transformation. So once the fit transform is done using scalar.fit transform x, we need to store the scalar values into a data frame. So we are applying pd.data frame on robust DDF, and we are defining the columns as x1 and x2. Okay, so the way we have done the creation of the data frame and fit transformation, we're going to follow the same logic for standard scaler and min scaler. So these are the lines where the code is for standard scaler and for min max scaler. Once we are done with that, we need to visualize this data, and we are doing subplots. So we need four different axes, one for the normal data, so that should be ax1, and the second is for robust scaler, third is for standard scaler, and fourth one is for min max scaler. Let's do that plot. So we are over here doing a KD plot. So for that, using Seaborn sns.kd plot, I'm calling the column x1 on the axis ax1, and color is equal to red. And for the column 2, which is x2, we're doing kd plot sns.kd plot, axis is equal to same ax1. That would be column 1, and basically axis for the figure, and the color is equal to blue. And let's set the title, which is after robust scaling, right? We should be able to see the data. And likewise, let's do the same thing we're going to be doing for standard scaler and min max scaler. And once we do the plt.show, So I'm going to skip through the outlier, right? And they're also not scaled to the same values. What happens after robust scaling? It removes the outliers, which is quite extent is removed, and even from the right hand side, the outliers are removed and they're superimposed at the same level. So we have quite scale data. So we are not seeing too much variance. While in standard scaler, the scaling happens between 0 and 1 so that the mean is 0, while we are not eliminating any outliers. So we still see the outliers on the lower um, uh, side. And also we see the upper quartile also, there is the outlier, which may basically having the skewed data, which would really impact our position of the scores that we might see from different methods that we're applying, whether logistic regression classifier or random classifier, right? So, and in min-max scaler, the scaling happens to the scale depending on the data, and also scaling happens between minus and 1. So that's something not we want to discuss, but we understood the difference conceptually. What is the difference of scaling the data using robust scaler versus standard scaler? So we understood the advantage, and we now are going to go back to our lecture and apply this technique of robust scaling, and then finally follow the procedure called to train, test, split the data, and finally do the predictions. I hope you enjoyed this lecture, and I'm going to see you in the next lecture. Thanks for joining. So we're going to continue this lecture. We saw in the previous lecture what is the distinction between a robust scaler and standard scaler. Let's start implementing that. So I'm importing the packages standard scaler, robust scaler from scalar.preprocessing. Let's instantiate the classes for standard scaler and robust scaler and assign to variables standard scaler and robust scaler. Once we are done with that, we're going to be doing the fit transformation. So I'm going to take the object robust scaler dot fit transform, and the column I need to transform is df amount dot values dot reshape minus 1 comma 1. So we're basically transforming this variable, scaling it using the robust scaler so that the outliers are removed both at the first quartile and above the third quartile. And also I'm reshaping the scalar values that's going to be returned from minus 1 to 1 column. So that's the intent of doing the reshaping. Same thing, I'm going to do the robust scaling for time. So I'm going to create a column called df scale time and do the fit transformation. The variable I'm going to pass over here is df time, the column, and dot values I need to reshape it minus 1 comma 1. Once we are done with that, we obviously don't need the columns time and amount. Let's drop them. So I'm doing df dot drop time comma amount x is equal to 1 in place of true. All right, so we are done with that, and the next thing is we're going to be assigning the variables df scale amount and df scale time, these two columns of the data frame, to different um, objects over here. So one of the object is scale amount, and for scale time it's scale time. Let's do that. And the reason I'm doing it because I want to bring these columns in the first index, so I'm going to first drop them. So that's the line number 4 in this cell. I'm dropping these columns again, df dot drop, and columns you can also specify columns is equal to the list of columns, which is scaled amount and scale time, x is equal to 1 in place is equal to true. Once we are done, let's insert at the index 1, which is the 0th position, df dot insert. We're inserting scale amount, that's the column name, and the object we're using is scale amount. Likewise, I'm going to do for scale time. So df dot insert, the index position I need 1, scale time, and yeah, and the column name is scale time and the object is scale time. So finally we can run df dot head. If I run this cell, we should see the output like this. So we have these two columns now as the first index and the second index, which is 0 and 1. Okay, so this seems interesting. Let's move to the next part. And the next lecture, let's do the assignment for the x and y. So let's also import the packages train test split. I'm importing from model selection, and also import stratified shuffle split from model selection. Once we are done with that, in my X, I need all the columns. That's my feature set except the class. So I'm going to drop the class, and rest I need all the columns. And for target variable, which I need the class variable, I'm just going to simply assign df class is equal to y. Okay, let's run this and next move forward. So now we can see that if I do df class dot value counts, I see the total population of non-fraud transactions is 284,000 and fraud transactions 492. Okay, so since we know the data is skewed, the very first part is we need to remove the skewed data from our variables which have negative correlation because of the skewed data. Okay, so let's do that. So in order to do that, let's shuffle the data. So I'm using a function called sample. So df.sample and I'm specifying frac is equal to 1. And now let's store the variables for fraud class and non-fraud class in different data frames because we want to get a distributed data frame. In order to do that, I'm doing a filter on the df, which is df.lock, and I'm passing df class is equal to 1, which should give me all the rows where class is equal to 1, so that we can store in fraud df. We know that that number is 492. We should get exactly 492 rows in fraud df. In non-fraud df, obviously we have more rows, 284k. We don't want to take all the rows. We want to filter it based on class is equal to 0, but at the same time we want to reduce a set to 492. So for that, once the filter is applied for class is equal to 0, I'm only taking 492 rows. So that way we have now the same set of records between fraud df and non-fraud df. Okay, right. The next thing is, so I'm going to remove this why we need 492 filters. So that was just to justify that. And now let's create a normal distributed data frame. And for that, I'm going to concatenate two data frames, which is fraud df and non-fraud df. Let's do the concatenation. Once we did the concatenation, let's also shuffle it. At line number 14, I'm taking normal distributed data frame and dot sample, and I'm specifying the random state which is 42, and that way we're gonna get the shuffle data frame. Okay, and let's run it. So if I do this data frame dot head, I got the shuffle data set. That's how you should be able to see the shuffle data set. Okay, now the next step would be to plot this and be able to figure out what is the negative correlation. Okay, so for that I'm doing plt dot subplot. My number of columns is 4 because I've already tested what are my columns which have the variances in terms of data skewness. So those are my columns V10, V12, V14, V17. And let's start with that because now we have the shuffle data. So what I'm going to do is it's going to be easy. I'm going to take the shuffle data frame and create the sns.boxplot for the variable called class. And my column is v10. My data is equal to shuffle data frame. So let me replace it over here. It's not going to be new df, it's going to be shuffle data frame. So, and let's set the title at axis equal to 1 0, which is 0 over here, and we're calling it v10 versus class negative correlation. Likewise, for other columns, we need to repeat the same thing and do plt.show. So let's see what happens over here. Now we can see that there is over here in every uh, x-axis for each figure, for each variable class, uh, for v10, v12, v14, we see there is negative data sitting away and we need to remove that. How are we going to do that? Let's follow a process, and let's start with importing the package called norm from scipy.stats. Okay, so also let's do another subplot. This time we need um, 3 subplots, so I'm going to do figure for ax1, ax2, ax3. I need on one axis 3 different charts, so I'm going to do 1 by 3, and figure size is equal to 20 by, let's say, 10. That should be okay. Now I'm taking my distributed data frame and I need to filter by class is equal to 1 where the fraud is. So I'm doing on my data frame, give me class is equal to 1, which is actually there. And for this B10 column, I need to see the distribution plot. So I would do cbond sns dot distribution plot for this data frame, which has for column V10 all the rows where class is equal to 1, where there's a fraud. And I'm using in this case axis is equal to 3, fit is equal to normal distribution, color is equal to green, and let's set the title as well, V10 distribution fraud transactions. Okay. All right, so same thing we need to replicate for other columns, V12, V14, and V17. I think that's going to be pretty simple for you guys. Just replicate this step and let's do the plt.show. What we see as observations, we can see that there is skewness of the data on on these columns, and that's our attacking point to be able to remove the skewness because it's not fully normally distributed data, right? In case of normally distributed data, I need to see my x-axis, both the starting index and end index pretty much same. So if you see even V14, there's a lot of skewness in this data. It doesn't seem to be normally distributed. Same thing for V12, it's not normally distributed. So in order to bring a normal distribution, we need to do certain steps, and let's look into those steps. All right. Okay, so now let's do another split of the data. Again, what we're going to do is we have distributed data frame for column 14, and let's uh, do the filter on class 1. We got the V14 as a fraud data frame. And now also calculate the first quartile and the third quartile. How we do it? It's quite simple. We assign two different variables, Q25 and Q75, and take np.percentile on that data frame because V14 is relevant to V14 column, right? To this data frame. And we pass in the argument 25 because we want the first quartile. And likewise, we want the third quartile, so we do np.percentile V14 column. For V14 column, or for this column, only one column, and all the rows, I need the third quartile, which is I'm passing 75 over here. So we can also print that in the next row. I'm printing the first quartile and the third quartile and formatting it Q25 and Q75. Once we have it, the very next step is to calculate the delta or range between third quartile and the second and the first quartile. Okay, so we got the range. We again going to print this range, and let's create a cutoff. I'm going to explain why we need a cutoff. We need to calculate the upper boundaries for V14. Likewise, if you see over here, V14 over here, we're going to calculate the upper boundaries and lower boundaries of this data. So somewhere we need to have first quartile over here, third quartile over here. So we need to skim this data. We need to skim this data over here on the first quartile. So for that, we are calculating a V cutoff, which is V14 range. If I multiply by 1, it's same, but I'm taking a higher factor to take a cutoff value. Once we have it, let's calculate the lower cap and the upper cap. V14 lower cap and upper cap is going to be first quartile minus the V14 cutoff. And for the upper cap, we're using the third quartile, which means third quartile plus the V14 cutoff. So that should give us the values for the V14 lower cap and upper cap. Let's print them. Okay, and now let's do the trimming part. So what I'm going to do is I'm going to create a list of outliers. For that, I'm doing a for loop in the data frame V14 fraud, and if I is less than lower cap of V14 and or is greater than upper cap of V14, I need to skim that data. That would be my list of all the outliers, and we can also print that. So printing that would require dot format and give me the length of all the outliers, and also print that formatted outliers over here. Okay, so we are done with that. And now in order for me to get the cleansed data out of V14, all I need to do is take the distributed data frame and again drop all the values of outliers that falls below the first quartile and the third quartile. Though we know what are the outliers, but we need to remove from the data frame. So in the line number 17, I'm doing a drop on the data frame, and the way I'm doing is I'm taking a distributed data frame, and for that column 14, I'm taking values anything greater than upper cap that needs to be dropped, and anything lower than the lower cap needs to be dropped. Once I have that, I have a distributed data frame based on 14 column. Likewise, we need to replicate the same logic to calculate the first quartile and third quartile for V12 column. For the class is equal to 1. We need to calculate the cutoff, and we need to calculate the lower cap and upper cap. Once you have the lower cap and upper cap, you can print the outliers, and also you need to calculate a new data frame, which is over here, the distributed data frame, which would involve dropping the values of lower cap and upper cap. So likewise, we're going to be doing for the other sets, which is column B10. And yeah, and I think it would be pretty easy to replicate this whole process. And if we run it, we can see all the values of cutoff, the range we got. The first quartile is -9 and the third quartile is -4. And the low cap for 14 is -17 and 3. And which would mean that if I have a um, if I have my data frame, in that my data frame I should not find values um, which are less than -17 and greater than 3. That's the intent of doing that. Okay, all right, so we have that and we are replicating the whole thing for other columns as well. So we're good with that, and we can see that total number of outliers over here, instance of outliers that we have removed is 951 samples, which is great. Okay, so that means our data is not skewed, outliers are removed, great. And finally we should be able to see that in the plot back again. So we're going to do the same thing now over here. We go to the subplot. I need 3 subplots on x-axis, so I'm going to do subplots 1 comma 3. My figure size is 22 by 10. Color scheme I'm using red and green, and let's do the first one. I'm calling cborn sns dot box plot for the class is equal to x, and my variable 14. I'm passing data is equal to distributed df on x is 1. I need that, and palette color I'm using the scheme based on the colors defined in the list. And let's set the title, which is we want v14 features removal of outliers. And let's do the annotation. In this annotation you can just follow the steps, because this is where we just taking certain coordinates of xy and xy text, so you can just bring it right over there. And likewise we need to replicate the same code for the column v12 v10, and let's do that and do the plt dot show. It's quite easy, right guys? Once we do that, we can see the output over here. This seems pretty good. We can see that all the outliers are skimmed over here. For v14, for v12, outliers are skimmed, and you can see the extreme outliers may be there in some cases v10, but pretty much our data is no more skewed. And now we can use this data set to build our train a machine learning model and do the classification for the fraud transactions. Okay, I hope you enjoyed this lecture, and I'm going to see you in the next lecture. Thanks for joining this lecture. Welcome friends to this lecture. So now we're going to be doing the training of our data. So in order to train the data, let's do some variable assignments. So we're going to be assigning to X the distributed data frame, all the features except the class variable. So let's drop that class variable and X is equal to 1. For target feature, we have class, so we're going to assign y is equal to distributed df class. And let's now import the package train test split from model selections. Once that is done, let's train test split the data. We call this package and pass arguments xy. Test size is equal to 20. You can make it to 33% or 30%. Let's say in this case is 30%. Random state is equal to 42. You want to keep that 42 just to make sure the results are same every time you shuffle the data. And that's going to be stored in xtrain, xtest, ytrain, and ytest. Okay, all right, so the next thing is the variable assignment into arrays. So let's do that. So we're going to take respective values of xtrain dot values, xtest dot values, ytrain dot values, and ytest dot values into the respective columns, which is xtrain, xtest, ytrain, and ytest. All right, so once this is done, this assignment, in order to feed into logistic regression and the other classifier, let's create a dictionary of the classifiers. We basically can do multiple classifiers as well. Like so right now we are using logistic regression decision tree, but you can add based on your knowledge curve that you want to play around with that. That's up to you. Like in homework, you want to treat that. All right, so let's assign the label to that, logistic regression for the class logistic regression, and decision tree classifier for the class decision tree classifier. Once that is done, let's call the package cross-val score from model selection, and let's now do the fit of the data and do the calculations for the accuracy score of the models. So very first thing we're going to do is we're going to create a for loop, just like a key value pair. Right now our key is going to be key, and value is a classifier over here, and we're trading through classifiers dot item. That's our dictionary. And let's fit for each classifier all the training features. So let's, and as well as fit the classifier with the test features as well. So let's first do the training score. So we're going to do cross-val score and pass in the arguments classifier xtrain, ytrain, and over here cross-validation. So since our data is more, we can do tenfold classification over here, and let's print the results. Over here the classifier in classifier.class name has a training score of and be passing training score dot mean, which we got in the upper line, and taking precision of 2 multiplied by 100, that should give us the accuracy score for the training data. Likewise, we're going to do for test score. So let's call the cross-val score has the same arguments. In this case, we're using the same classifier, but uh, we need our test features. So we're going to be calling x test and y test, and let's reduce the number of cross validations to 5 over here. Okay, so we got the test score. Now let's print the accuracy. So print the classifiers. So we have two classifiers, which is logistic and decision tree, and basically that we can invoke through classifier.class.name. And let's do the evaluation of the test score. So test score dot mean, we're taking the mean value of the test score, the precision of 2 multiplied by 100, and if we run this, we should see something like this. Okay, so we can see for the training of the logistic regression, the score is 95, but it drops when we do the tests. So we get it to 90%. Likewise, for decision tree, our training score is 92%, but at the time of the test data, it drops to 85% because we have less amount of data. Remember that we were using almost 492 records, and since we are testing at 40 odd records, the accuracy is supposed to drop. That's fine, but if we have homogeneous data and much larger data set, that probably our test score is going to be much higher. But right now you can compare these two different classifier score, and you can use the model which is giving a higher accuracy. In this case, I would like to retain logistic regression, but in general it is giving me a higher score. But if we look at the totality, typically decision tree or random forest classifiers have a higher accuracy score because it allows you to prune the data to different leaves, and you can do multiple ensemble approach in terms of calculating the mean values of a decision tree classifier. Okay, so I think this was interesting lecture. I hope you enjoyed this lecture. I'm going to see you in the next lecture. Thanks for joining. Welcome friends to this lecture. So in this lecture, we would learn how to get the best params for the decision tree as well as for the logistic regression. Alright, so in order to do that, let's import the package called grid search CV from sklearn.model selection. Basically, grid search CV is a technique to find optimal parameter values from a given set of parameters in a grid. And let's define that grid. So I'm creating a logistic regression grid where I'm leveraging penalty as a list of L1 and L2, and these L1 and L2 are nothing but Lazo regression penalty parameters, and L2 is a ridge regression penalty parameter. And the way they operate is quite simple. Basically, L1 tries to shrink the coefficients to 0, while L2 tends to shrink the coefficients evenly. So that way we would know that which parameter in the key feature plays a bigger role in the prediction. All right, and see the list of all the penalties that we have defined, so you can pass this list. And then the very next step, I'm calling the class grid search CV and passing the method logistic regression, and also passing my logistic regression params list, right? Once that is done, let's fit the training and training and target variable, which is x train and y train. And finally, we're going to call the best estimator on the LG object, and let's store that in log params. Once we are done with that, let's proceed with the decision tree classifier. I'm following the same technique for decision tree classifier over here, and I'm also creating a dictionary for criterion, which is Gini and entropy. So if you remember from my previous lectures on the decision tree, then Gini is nothing but impurity, and it's a function that determines how well a decision tree can be split, right? Basically, it helps um, the decision tree algorithm to determine which split is the best, that it can build a pure decision tree out of that, right? And similarly, entropy is also another technique to prune the different nodes in the tree, and it basically is used to measure the order of the disorder, basically. So it tries to measure how much disorder is there, so the decision tree algorithm can make a mathematical calculation on the entropy, and that would allow to make right decision to go on the left node or the right node, or which node to choose to traverse. Okay, And likewise, I'm defining the max depth, which is a range of 2, 4, and 1. Minimum sample leaf is, I'm giving a range 5, 7, 1. And let's again call the grid search CV class. And over here, I'm specifying decision tree classifier method and passing my dictionary for decision tree parameters. Let's do the training. Once I do the train parameters, X train, Y train, I should be able to fit these parameters to GT. And let's basically call the um, our best estimator method on the decision tree object GT, and that would allow us to store the best parameter in three params. Okay, and in the next cell, what I'm doing is I'm printing this. Once I run this cell, you should be able to see what are the best params that would give us the maximum score. So in case of logistic regression, I am getting a penalty of 0.1, while in decision tree classifier, if the tree uses the criterion either Gini or entropy, the max step should be 2, minimum sample leaf size should be 5. All right, that's the way we calculate in the best parameters, and you can use these best parameters to again use the scoring techniques to find the best score. That's the whole objective of doing the evaluation of the best parameters. All right, friends, so I hope you enjoyed this lecture and you have a fundamental knowledge of evaluating the best parameters. And thanks for joining the lecture. I will see you in the next lecture. Thanks.